Welcome, this is Coach Dorf. We're going to continue our discussion about calculus, and this time we're going to talk about related rate problems. Now, when we've talked about derivatives, we've talked about derivatives in terms of the slope of the tangent line. What that means is that if we have the graph of a function, such as this blue line here, y equals f of x, and there is a point, x equals a, we look at that point on the curve, and we now draw the tangent line to that curve. That slope of that purple line is equal to the derivative of the function at the point A. So that's kind of a geometric way of thinking about these things, and it fits very well with the definition of the derivative. Another way of thinking about the derivative is that it equals the velocity or speed of an object if the original function is its position. We saw some of this in the previous video when we were dealing with throwing an object into the air. So, and the function then represented the height, the derivative then equaled the velocity or speed of the object that was thrown into the air. A third way is rate of change. And this is the most general way, and it's really a cool way to do it because it applies to lots of different problems. We saw some of that in the previous section, previous video. Today, though, we're going to talk more about this idea of rate of change. And in particular, we're going to talk about things that are called related rate problems. And related rate problems are when we determine the rate of change of one quantity in terms of the rate of change of another quantity that it's related to. All right, that's why it's called related rates, because the rates of change are dependent upon each other as we do these problems. All right, so let's look at an example here. Consider a circle of radius r and area a. Suppose the radius is increasing at a rate of 3 inches per second. How fast is the area increasing when the radius is 5 inches? Now you can think of this as an example of suppose you have a body of water. It could be a lake, a pond, and it's starting to rain. And as the raindrops come down and they hit the water in the lake, they form a circle, and that circle increases in size through time. So the size of the circle and the radius of the circle are both increasing with time, and they're dependent upon each other. As the radius increases, the area increases. So this is a good example of a related rate problems, because the one quantity, the radius, is increasing. That also then affects the rate of change of the area at the same time. So how would we solve this problem? Well, first I draw a picture. Here's my circle, radius r, and A is the area here. And what I want to do is I want to get a formula that relates area and radius. Those are the two variables I have, radius and area. What's a formula that relates those two? Well, the formula is area equals pi r squared. Now, when it talks about the radius is increasing at a rate, that the idea that it says rate there, so radius and the rate there means that we're going to have a dr dt. As time increases, the radius increases. If the time decreases, which I'm not sure how that would happen unless we go back into the future or back into the past, then the radius would decrease. So, but the radius is changing with respect to time. And that's what comes in here when we say radius is increasing at a rate of 3 inches per centimeter. And we can put that then as the amount. Radius, dr dt is 3 inches per second. What else is changing? Well, the area is changing with respect to time. And so that's going to be the a dt. And that's what we don't know. That's what we're trying to find. All right. So again, we have these two rates, the rate of the radius changing and the area is changing. That's why we have a related rates problems, because they're both dependent upon each other. They're both rates of change. And we can represent the radius changing as dr dt and the area changing as dA dt. So what are we going to do? Well, we're going to take our formula, area equals pi r squared. And because we have rates of change here, we're going to take the derivative, because that's what the derivative, one interpretation of what the derivative means, the rate of change. So when I do that, I'm going to do d dt of a equals d dt of pi r squared. Why do we use a t as my variable there? Because the area is changing with respect to time, and the radius is changing with respect to time. So that's what the variable is. As time increases, area increases, and radius increases. All right, when I do that, then I get a dA dt on the left, and on the right, my one variable is r. Pi is not a variable, it's a constant. So I'm going to take that derivative there, and by the power rule, the derivative of pi r squared with respect where r is my variable is going to be 2 pi r, and then I'm going to have a dr dt. And what do I then have? I'm trying to find this, trying to find dA dt. This is what we want. We know that r, in this problem, it says r is equal to 5 inches. So this is equal to 5 inches. And this, dr dt, we had was 3 inches per second. So when we substitute those in, then we have dA dt equals 2 pi times 5 inches times 3 inches per second. And when I multiply those together, then I get, on the right, we get dA dt is equal to 2 times 5 times 3, which is 30. And then we've got my pi. And my units are inches squared per second. And that's my answer there. We see that my units, I have 2 units of inches there. I've got that inches and I've got that inches, so I get an inches squared. And then in the denominator, I've got a second, so I've got a second there. So those are my units there. All right, is this reasonable? Let's just check this. Does this make sense that this could be? Well, remember that we're going to be looking at when r is 5 inches. What is the area then? Well, the area is pi r squared, so that's going to be 25 pi. Let's look at 1 second before that. Now, the rate of change is 3 inches per second. So if I go at 1 second before that, that means then I'm going to have 3 inches less. So then in that case, r is going to equal 2. So this is 1 second earlier. I'm going to get the radius is equal to 2 inches. And so then the area is going to be pi r squared, which would be 4 pi. And let's look at 1 second later. So it's increasing at a rate of 3 inches per second. So at 5 inches, if I do 1 second later, it's increased by 3 inches, the radius. So then it's 8 inches. And the area then is pi r squared, which would be 64 pi. Now, what do we notice about these differences here? What's the difference? The growth between 4 pi and 25 pi, that's 21 pi. And what do I notice about the growth between 25 pi and 64 pi? That is 39 pi. What's halfway in between those? So halfway between 21 pi and 39 pi is, okay, we have a drum roll here, please. It is 30 pi. That matches our answer. Now, it doesn't mean that doesn't prove that my answer is right. The proof of it, or the validation that my answer is right, is the work that we did that's shown right here in purple. But the blue shows us that it's reasonable, that the answer I got in purple is reasonable. All right, let's look at another example here. All right, a plane is flying horizontally at an altitude of 1 mile and a speed of 500 miles per hour and a speed of 500 miles per hour, and it passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when the plane is 2 miles away from the station. All right, so let's look at a diagram or a picture that relates this. So I have a plane here, and we'll just say, here's my plane, and try to draw a plane, kind of like a plane there. There's my plane, and it's flying horizontally at an altitude of 1 mile. So that means the height above the ground is 1 mile. All right, and the speed is 500 miles per hour. Now, speed is the derivative. So let's put in a variable here. We'll call this a here. And so we know that the AT, that's the speed of the plane, is 500 miles per hour, right? All right, then we're supposed to find, let's see, the distance from the plane to the station. So let's draw the station in here. The station is going to be right here. I don't know how to draw a radar station, so we'll just put a box there, call it the radar station. And we're supposed to find the distance from the plane to the station is increasing. So where is that distance? Well, that distance is this diagonal line here. So that's the distance from plane to the radar station. And let's call that something. We'll call that C. All right. So we want to to find dc dt. Find the rate at which the distance is changing. So it's not finding the distance, but we're finding the rate that the distance is changing. And that's why we have the derivative there, dc dt. And we want to find that, let me erase that question mark. We want to find that when c is 2 miles. So that comes from this, from here, when the plane is 2 miles away from the station. All right. And just a correlate thing, the speed of the plane is equal to that there. So we get that from, we want to find dc dt. So now what we need is a formula. We need a formula relating A and C. Well, I look at this diagram that I've drawn, and my thinking is we've got a right triangle because this angle is right here. Because we go, the height is one mile, or the altitude, and it's going, the plane is flying horizontally, so that's flat. So there has to be a right angle there. And I think of Pythagorean theorem. And the Pythagorean theorem would say a squared, this says a squared plus 1 squared equals c squared. Or I could write that as a squared plus 1 equals c squared. Because I now have, I want to find dc dt, and I've given dA dt, I'm going to be taking derivatives because that's what I do. I mean, when I want a dA dt, that means I've taken the derivative there, and it relates because we have speed. All right, we're trying to find the speed of the plane is given as dA dt. We're trying to find the rate of change, which is derivative of the distance between c and t. Notice also that this is a related rates problem because as A changes, as A gets larger, C gets larger. All right. So as the rate of the speed of the plane changes, then also the distance would also change between the rate of change of the distance between the radar station and the plane. So it's a related rates problem. So we're now going to use this version of Pythagorean theorem we have here, plugging in our variables, and we're going to take the derivative. And we're going to do it with respect to time because everything here is affected by time. As time changes, A changes and C changes. So I'm going to take ddt of everything. So I have ddt of A squared plus ddt of 1 equals ddt of C squared. And when I take that derivative then of A squared, 2A dA dt, the derivative of 1 is 0 because 1's a constant. And then I take the derivative of C squared, I get 2C dc dt. And I notice that everything has a 2, so I can cancel out the 2, but you don't have to, but you can do that. And what am I trying to find? I want your dc dt. Well, here's my dc dt. That's what we want. So I'm going to go ahead and rewrite this by dividing everything by c. So I get a over c dA dt equals dc dt. And that's what we want. And now we're going to plug in our values. What do we know? Well, we know that the A dt is 500. So this is equal to 500, and that is miles per hour. Also, I know that E is 2 miles. So C here is 2 miles. But it doesn't say anything about what A is. So what is A? Well, it doesn't tell us that explicitly. So we have to do a little bit more work here. Remember that we have this right triangle, and this was 1, this was C, and this is A, and that gave us then the formula A squared plus 1 squared, or 1 equals C squared. And we know that E is 2 miles from this there. So then we can solve for A. So A squared is going to equal 4 miles squared, but we'll just use 4 there. And then we're going to subtract the 1, we get 3. So then A equals, when I take the square root there, so if A squared equals 3, then A could equal plus or minus square root of 3. But since we're dealing with real distances here, we're going to just say that the distance there is the square root of 3, and that unit there is miles, because everything is in terms of mile. So now we have A, and we can then substitute that back in here. So what do I have? Again, I'll write my formula of AC, A over C times dA dt equals dc dt, and A is square root of 3 miles over C, which was 2 miles. Then I'm dividing it by 500 miles per hour. And when I do this, some things cancel out. My units miles here cancel out, and I can read and then write this as 500 square root of 3 over 2 miles per hour. And then I can reduce the 100 over 2, that would be 250 over 1. And I then get 250 square root of 3 miles per hour. And that is what my rate of change of the distance between the station and the plane. So it's not the distance changing, but it's the rate of change that's demonstrated by that. Okay, look at another example, a third example here. So in this one, we have the base of a triangle is increasing at the rate of 8 centimeters per second. The height is increasing at a rate of 3 centimeters per second. When the base is 20 centimeters and the height is 10 centimeters, how fast is the area of the triangle increasing? All right, so let's look at this problem. We'll first draw a diagram. So I have here, a triangle, looks like that. Okay, quantity here, let me do this in some colors here. This represents height of the triangle, and we'll do this as the base of the triangle. And what do we know? We're going to call the base B, and we're called it height, and we've got the area. You're supposed to find the area of the triangle, so we'll call A area. And what information am I given in this problem? Okay, it says here that the height, the base, so we're going to do purple here for base. The base of the triangle is increasing at a rate of 8 centimeters per second. Okay, but it talks about rate there, so that's a derivative. So it's going to be dB dt equals 8 centimeters a second. All right. The word rate then tells me it's a derivative because it's a rate of change. Variable for my base is B, and it's with respect to time because time is what's changing here. All right, then I'm also given that the height is increasing at a rate of 3 centimeters per second. So the h dt, the rate of change there, because it's rate again, is 3 centimeters per second. All right, and it says then when the base is 20, so when B is 20 centimeters, okay, we do that, 20 centimeters. And we're given height is 10 centimeters. 10 centimeters. We're then supposed to find how fast the rate of the triangle is increasing. How fast tells me it's a rate there, okay? Not how much, it's not the amount of the area, but it's how fast the area of the triangle is increasing. So that's going to be dA dt. That's what we want to find. All right, so what do we need? We need a formula relating these different units, relating base, height, and area. Well, but what's that formula? Well, it's the area of a triangle. But the area equals 1/2 base times height. And because we're finding rates here, rates of change, and all these rates of change are dependent upon each other, okay? Height is changing at a certain rate and the base is changing at a certain rate, then that change, those rates of change then affect the rate of change of the area. And that's why it's a related rates problem, because the rate of change of base and the height, the rate of change of the area. And so they're related to each other. All right, so I'm going to take derivatives here. I'm going to do black here. I'm going to do take d dt of sides. So I'm going to have d dt of A on the left and d dt of 1/2 base height. Okay, on the left, I've got dA dt. That's pretty straightforward. What do I notice about on the right? Well, I don't have just one variable. I have two variables here, right? I've got B and A. There are two variables. So I have to do the product rule in order to take that derivative there. So the 1/2 is a constant, so that I don't need to take the derivative of that. I can just bring that out front. So then the product rule says it's the first B times the derivative of the second. So that would be the dH dt plus the second times the derivative of the first, which would be dB dt. So we have that. There's our formula then that we've got here. And let's see what we have here. We've got is 20, so that's going to go in here. The h dt is 3, so that's going to go in there. H is 10, that's going to go in here. And we have dB dt is 8, and that's going to go in here. Okay, we're just going to go ahead and do that. The A dt is going to equal 1/2, all right? B was 20 centimeters. The H dt was 3 centimeters per second. H is 10 centimeters, and the dB dt is 8 centimeters per second. Okay, then we get dA dt 1/2, multiply those together. 20 times 3 is 60. Notice I have my centimeters over seconds. So I'm going to have centimeters squared over seconds. And then for the second part, I've got 10 times 8, which is 80. And that's also going to be centimeters, circle those in there, centimeters squared per second. Notice also that in the step before, all my units, they match up here. I've got this centimeters over seconds, centimeters over second. If I'm going to add those things together, the units should be the same, and they are, right? They're centimeters squared per second for both of them. Okay, for the problem then, we have the A dt is 1/2, and then I add the 60 plus the 80, that's 140 centimeters squared per second. Okay, and that then it gives me 70 centimeters squared per second. And that's my answer. And this makes sense. When something is, this makes sense, also makes sense in terms of the units, is what I was referring to. I have something that is linear. That means it's going in either up or down or left or right. Then the rate of change there should be 1 unit over seconds, or it's over the time thing. So it should be centimeters over second. Because I'm going one direction, the exponent on the centimeters should be 1. When I do area, I can go in 2 directions. I can go vertically. So there, my units should be squared. So I should have centimeters squared, which is what I do have here, right? Centimeters squared, because area is a 2-dimensional object. When I talk about volume, that will be 3-dimensional object. I should have something cubed then for compared to the rate of time there. So if something is length, then it's 1-dimensional, area is 2-dimensional, volume is 3-dimensional. Okay, let's do another example. All right, in this example, we have cyclists start moving at a constant speed from the same point. One's traveling north at 15 miles per hour, the other's traveling east at 20 miles per hour. Determine how fast the distance between the cyclists is changing. All right, so let's look at this problem. First thing I would do, again, done in all of these, is I would draw a diagram. So you have two cyclists that start at the same point. We'll say that's the point they start at. One is going north, so this is the north direction, we'll say. One is going east here, going east, and north and east are separated there by a right angle, so that's really good here. I'm gonna call this side A and this side B, all right? And what do we know? We're given that they start moving at constant speeds. Well, the one that's traveling north is going at 15 miles per hour. That's the speed. What is speed in terms of derivatives or in calculus? It's the derivative. So that means the A dt, the derivative of A, is going to be the speed of the bicyclist or the cyclist traveling north, and that's going to be 15 miles per hour. All right. The one that's traveling east is going at 20 miles per hour. Okay, that's the speed again. So speed is derivative. So we get dB dt is 20 miles per hour. Okay, fast is the distance between, how far is the distance between the cyclists changing at noon. So where is that distance between the cyclists? That's this distance here. So this is the distance between the cyclists. Let's see if I can spell cyclist here. Yes, okay. So, and we're going to call that C. All right. Randomly picked A, B, and C. No, I didn't randomly pick A, B, and C. Why did I pick A, B, and C? Because you should be thinking Pythagorean theorem there. All right. What are we supposed to do? We're supposed to find how fast, so fast in there, the distance between the cyclists is changing at noon. It's not asking what is the distance between them, but it's asking how fast is that distance changing. So want to find the C dt, okay, at noon. Now we're going to need something for A, B, and C there, some values, but we'll come back to that. So we need a formula. So we draw a diagram on all these problems. It's very similar. We draw the diagram. Then we look at the units that are given us, the information that's given us, and then we find a formula that relates those knowns, those variables. Okay, formula, that's what we need. That's relating A, B, and C. Okay, I shouldn't put a question mark here, so I'll erase that. The formula relating A, B, and C, well, that's the Pythagorean theorem. Okay, we've used before, and that's going to be A squared plus B squared equals C squared, which is why I used A, B, and C for my sides there. But you could have used X, Y, and Z, or you could have used wanted like Christmas tree, smiley face, and heart. Those will all work also as variables. Okay, because I'm talking about speeds here and rates of change, we're going to take d dt of everything. Let's see if I can spell here. Okay, start over again, of everything there. Okay, let me just stop for a moment and point out that the process in solving all these problems is very similar. The first thing we did was draw a diagram and we labeled our variables. Then we wrote down what was given to us in the original problems in terms of the variables that we used. Then we had to find a formula relating all those variables. And then we take the derivative of everything there, of that formula. Okay, we're taking the derivative because these are rates of change, because we have speeds or rate of change or how fast something is changing. So all these are very similar in that type of approach. What's different is the problems are stated differently. That's what makes these problems can make them really hard. Okay, we're going to take d dt of a squared plus d dt of b squared equals d dt of c squared. All right, and when I do that, I get by the power rule 2a dA dt plus 2b dB dt equals 2c dC dt. And some of you will notice I can cancel out the 2's automatically, but we'll wait a little bit before we do that. But if you want to do that, go ahead and do that. That's what I would do. But to show why we can do that, I'm going to wait a little bit. And remember what we're doing here. We want to find dC dt. That's what we want. And here's my dC dt. So I want to move this to the other side, so I get c dt by itself. So what I'm going to do is divide both sides by 2c. So I have 2a dA dt plus 2b dB dt over 2c, and that equals dC dt. Now what I'm going to do, I don't normally show this step, but I can. In the top, I can factor out a 2 because everything has a 2 in common, and I get then this quantity over 2c, and that equals dC dt. And because I have the 2 multiplied in the top and a 2 multiplied in the bottom, I can cancel those out. All right, and I get a dA dt plus b dB dt over c equals dC dt. Now you don't have to show that this step that I just did here. Okay, you can just go from here to here. I just wanted to justify it so that everybody sees that's how I do it. If I didn't have, if on the other hand, if I had something like this, okay, back here, have something like this, as b dB dt over 2c, I cannot cancel out the 2 here. I can't go like that because there's no 2 in front there. So this is not correct thing to do. Okay, now I'm just gonna, the last thing is, and I substitute in the values. All right, so let's see, what are we given? Remember, we have ddt was given as 15 miles per hour. Okay, we were given dB dt is 20 miles per hour. We want dC dt at noon. So we're not given A, B, and C, but we can figure out A, B, and C by knowing that we're at noon. When did we start? Well, the original problem says we started at 10 a.m. and then we go to noon. So that's 2 hours. Okay, this is 10 a.m. to noon equals 2 hours. So they've been riding for 2 hours. What does that tell us then? Well, since the dt is 15 miles per hour and we have 2 hours, so after 2 hours, A is going to equal 15 times 2 or 30 miles. That's how far A has traveled. 15 miles per hour, 2 hours. Multiply the 15 miles per hour times the 2 hours. Hours cancel out and you get 30 miles. Then likewise, since dB dt equals 20 miles per hour, okay, 2 hours, then what's B going to be? B is going to equal 40 miles. Okay, 2 times 20 is 4. All right. What about C? Well, we don't know the rate of C because that's what we're trying to find. So we can't do the same approach. We can use Pythagorean theorem again. So remember, we have this, looks like this. Here's A, right triangle, B and C. And we know that is equal to 30 miles. B was equal to 40 miles. So what is C? Well, by Pythagorean theorem, this is 30 squared plus 40 squared equals C squared. Okay, squared is 900, squared is 1600, C squared, 900 plus 1600 is 2500. Take the square root of that. I'm only interested in the positive square root since we're doing with distances. Square root of 2500 is 50, and so that's what C is. Okay, C is 50 now. So we've got everything here. We've got A, B, and C, and we've also got these rates here, the A dt and the B dt. So now we're going to plug that into that formula. Okay, recall we have the formula. I'm going to put dc dt on the left side now, but it still is the same. I have A times dA dt plus B times dB dt over C. That was my formula from another different color in here. From this, I'm just bringing that down here. Okay. When I plug those values in, I get A is 30 miles, dA dt is 15 miles per hour plus B, which was 40 times 20 miles per hour over C, which was 50. And when I simplify that, solve this, I'm going to not show all the work here, but when I do that, I'm going to end up with, here. When I do that, I am going to end up with 50, it's going to be miles per hour. Okay, that's going to be my answer there. Could show all the work. I'm not going to show it right now because I'm running out of space because I have my next problem on the next page here. But you can do it, you can calculate it out, and you can also check that the units are right. We've done in the past, very similar to the type of this. The difficulty usually is not going from the numbers to the final answer. It's getting all the preliminary work that we just did to get that. Okay, example I want to show is this one right here. All right, gravel is being dropped a conveyor belt, and it forms a pile in the shape of a cone whose base radius is twice the length of the height. Okay, height is at 4 then. Height of the pile is increasing at a rate of 0.5 feet per minute. And then you're supposed to determine how fast is the volume of the gravel pile increasing at that moment. Okay, like in the other problems, what do we do first? We draw a diagram. So here's my cone, here's my radius, base radius, and here's my height there. All right. And it says the base radius is twice the length of the height. Now this can be really tricky. How do I write that? What is the relationship between R and H? If the base radius is twice the height, the height value. Okay, let's think about that. Let's think of some numbers. The base radius is 4. Then what's the length of the height? Well, the base is twice of it. So if it's 4, then the height has to be 2. All right. So if R is 4, H is 2, because 4 is twice. R is 6, then the height is 3. If R is 8, then the height is 4. Okay, the radius there is always twice as much as the height. So how does this then relate? What do I have to do to compare these two? Well, sometimes students want to put a 2 in front of the R, but that's not right. It should be a 2 in front of the H, right? Because then it makes sense. If I have R is 4, like we had right here, then H is 2, then 2 times 2 gives me my 4, and it works out. So make sure that you get this correct. You don't put 2R equals H, but it's R equals 2H. Okay, we're given that. And is when H is 4 feet, height of the pile is increasing at a rate. Let's use a different color here. Okay, H is 4, the height is increasing at a rate. So it's increasing at this rate of 1/2. And we've got rate in there. So that means it's going to be a derivative. So I'm going to have dH dt equals 1/2 feet per minute. Also know that I should have derivative in there because I've got 1/2 feet per minute. So when you've got the time in there, you're going to have the dt there in the denominator. So it's going to be dH dt because I have feet per minute. When I don't have derivative and it's just feet, then it's going to be h. There's no dt there or no derivative there. Okay, we know that when h is 4, dH dt is 1/2. And you're supposed to find how fast the volume is increasing. So find v dt, all right? How fast the volume is. Fast tells me it's a rate. Again, this is a rate of change problem because as the height and radius change, if they have a rate of change there, then there's how fast the volume is changing. So if we look at how fast the height and radius are changing, that determines, or its effect that influences how fast the volume is changing. So those related rates, or those rates of change, are related, and that's why this is a related rates problem here. Okay, now we've got our variables, we've got our picture, so now we need a formula that relates h and r and v, which is volume. Well, that's going to be volume of a cone. And the formula for the volume of a cone is going to be 1/3 pi r squared h. That's what the volume of a cone is. Now, should you know that one? The example of formula I don't think that you should know. So I think in many cases, a problem like this, you'll be given this formula. You should know Pythagorean theorem, you should know area of a triangle, you should know area of a rectangle, types of things you should know. But when it gets a little bit complicated like this, volume of a cone, I don't expect that you should know that one. So it will be given to you on this one. Okay, now we're going to take d dt of both sides here, formula. Why are we taking derivatives? Because we're doing rates of change, and we want to find dv dt, so we have to take d dt of the volume to do that. Okay, now this is where I think a lot of people would get to this point, and on the left side, it's very clear what we have. Now on the right side, it gets a little bit more complicated here because I have variables. I have my r and my h. So you might think I need to do the product rule, but remember there's a connection between the radius and the height. The radius is always twice as much as the height, okay? Remember, radius is twice as much as the height. So we figured out earlier that meant that r equals 2h here. So we can use this and substitute this in to get rid of one of the variables, okay? We substitute this in to get rid of one variable, all right? And that will make the derivative easier to do. And we can do this again because there is this relationship between the radius and the height. The radius is always twice the height, which means r equals 2h. All right. So now the question is, which one do we want to get rid of? Do we get rid of r or h? That's really important. Well, let's go back and look at what we're given here. If I look at my problem, okay, we have r equals 2h. We have 8 when h is 4, the h dt is 1/2. That is really important. Okay, it's important because this tells us to keep h as our variable because we have a value for h and we have a value for dH dt. So we want to get rid of r since we have h equals 4 feet and dH dt is 1/2 feet per minute. We're given these things, so we want to get rid of r. Okay, we're going to redo that then. The volume, do this in black here, volume is 1/3 pi r squared h. So we want to substitute in what r is. So r was 2h. We put that in there. Again, that comes from here because r equals 2h. We're going to substitute that in here to get those parts. And so then I can write volume as 1/3 pi 4h squared h, for volume equals 4/3 pi h cubed. So now this is much better because we only have one variable and we have things in terms of h and dH dt. So now take d dt of this formula. Okay, and we have d dt of v and d dt of 4/3 pi h cubed. And on the left, I get dv dt, which is what we're trying to find. And now I take the derivative of the right side. H is my variable. So by the power rule, I bring the 3 out front. So I get 4 times 4/3 times 3 times pi h squared dh dt. Okay, and be written, then dv dt is 4 pi h squared dh dt. And we'll substitute in what we have. Know that here was 4. Let me redo that here. In purple, h is 4. So we're going to put that in here. So this is h equals 4. And we know that the h dt is 1/2. So we're going to put that in here. The h dt is 1/2. So doing that, we get dv dt equals 4 pi. We get 4, and my units there were feet squared. And then I have my dh dt, which was 1/2 feet per minute. Okay, then dv dt is 4 pi times 16 feet squared times 1/2 feet per minute. And I combine those together and I get 4 times 16 over 2 times pi. And then my units are feet cubed or cubic feet per minute. And just cleaning that up, times 16 over 2, 4 times 16 is 64, divided by 2 is 32. So I get 32 pi cubic feet per minute, and that becomes my answer. Notice, as we mentioned earlier, we've got cubic feet and we're dealing with volume. Volume is 3 dimensions. Okay, you've got the base, and so that gives you 2 dimension because you have area, but then you put in the 3rd dimension height, and so you get 3 dimensions there. So that's why you should have cubic feet per minute. All right, hope that helps you understand this. Have a great day.